today we have covered chapter 0, 1, and 2 over the last couple of weeks, and we also covered chapter the Jordan canonical form of all undergraduate level informations, and we also learned how to find generalized eigenvectors. So we now know how the Jordan canonical form works and how to find Q and J for a given matrix that makes Q inverse AQ is a Jordan canonical form. Today we go for the general case of canonical forms. Okay. Two similar matrices have same trace and same determinant and same characteristic polynomials and same eigenvalues. But as you see here, these two matrices are not similar, even though these two by two matrices have same trace and same determinant, same characteristic polynomial, and same eigenvalues. But still, they are not similar. By Schur's theorem, we know every matrix is unitarily similar to an upper triangular matrix. But this upper triangular matrix is not unique. It's not unique. Okay. So, yeah, we will investigate how we can find a similar matrix which is simpler as much as we can. Okay. Okay. So, we try to find an upper triangular matrix form that is as nearly diagonal as possible, because all diagonal matrices are the exception for the analysis that we had in a previous page up to isomorphism. So we like to have the upper triangular form as nearly diagonal as possible. This result is called the Jordan canonical form. A Jordan block, JK of lambda, is defined in this way. Diagonal entries are all this lambda here, and super diagonal entries are ones, and all others are 0. A Jordan matrix J is a direct sum of Jordan blocks, like this. And the addition of the size of all these Jordan blocks is same as the size of this Jordan matrix. Okay, Jordan canonical form. Okay. Suppose A is a direct sum of these block matrices. So it's a block diagonal matrix. The first theorem says A is diagonalizable if and only if every block matrices AIs are diagonalizable. This is an if and only if statement. If this matrix A, which is the direct sum of these block matrices, is diagonalizable if and only if each blocks are diagonalizable. Okay. We use math induction on this proof. So we first show for the case with 2 blocks only. Then we can easily extend it to the general cases. Okay. One direction from here to here is like this. Since each AI, the block matrix AI, is diagonalizable, there exists a matrix S1 and S2 that makes a diagonal matrix corresponding to each AIs. If we form another matrix by direct sum of these 2 matrices, and we multiply that block matrix as and find the S inverse AS, which is this form, then we can easily check it is a direct sum of 2 diagonal matrices, which is a diagonal matrix. Okay. What that means is this matrix, which is A, is diagonalizable. So one proof one side is very easy. Okay. Next, the other direction. Suppose this direct sum of block matrix is a diagonalizable. We show each of these are diagonalizable. Let A1 has a size k by k, and A2 has a size n minus k by n minus k. Okay. Then, since A is diagonalizable, there exists n linearly independent eigenvectors of A. Let's say x1, x2, to xn. And we partition each of these vectors in this way. The first k terms and the remaining of it. We give the index as this. Okay. So this is a small, the k by 1 vector, and this is n minus k by 1 vector. Then, since that those were the eigenvectors, so the eigenvalue is satisfied this characteristic equation, and if we rewrite it, then we can easily check this k by 1 and this n minus k by 1 vectors are same as this, respectively. What that means is every xi1 is an eigenvalue, eigenvector of A corresponding to the eigenvalue lambda, and this xi2 is an eigenvalue of A2 corresponding to the eigenvalue lambda. Okay. Okay. We want to show that each of these AIs are diagonalizable. Slow already. show those vectors. Okay, here, here. 그래요, 아직도 지금 막 시작했는데 왜 이렇게? Okay. First, each of these vectors, x1 to xn, are non-singular. It's a linear independent. So the matrix whose columns consists of those vectors, linear independent vectors, are non-singular. Okay, so this submatrix, first k rows with all others, and the last n minus k rows with others has rank k and rank n minus k. What that means, it has k linear independent columns. This submatrix has k linear independent columns, and this submatrix has n minus k linear independent columns. That says A1 has k linear independent eigenvectors, and A2 has n minus k linear independent eigenvectors. Since the size of this matrix k by k that has k linear independent eigenvectors, so A1 is diagonalizable, and same thing for the A2. So A2 is also diagonalizable. This is the proof. Okay. Use that to show for the general by using the mass induction. Okay. Assume true for all s less than k, then we show it is true for the t as well. That this is, we have this, we add the very last one on that. The arguments are working exactly the same as we see here. So the proof is very basic. This is going to be an exercise. Okay. Next theorem. Okay. Theorem 2. If A is non-trivial Jordan block, if A has a non-trivial Jordan block, then A is not diagonalizable. It's not diagonalizable. This non-trivial Jordan block means it is a Jordan block whose size is bigger than 1 by 1. Suppose we have a non-trivial Jordan block, the matrix A, then it cannot be diagonalizable. Okay? All you have to show for this is all you have to show is we show in case the matrix has a non-trivial Jordan block, then the matrix A cannot have the linear independent eigenvectors, not as many as the size of that Jordan block. Then the proof is done. Okay? Because the if and only condition for the diagonalizability is the existence of full linear independent eigenvectors. If it is short, then we can always tell that the matrix is not diagonalizable. suppose Jn of lambda is a non-trivial Jordan block. We just show for that particular one block. Then we can show this Jn of lambda is not diagonalizable. Let's say the size is n for that particular one. By the way of contradiction, suppose this Jn of lambda is diagonalizable. Then there exist n linearly independent eigenvectors. And it satisfies these characteristic equations. What that means is this. If we just subtract the right term on the both sides. But these xi's are all linear independent. And the number of those linear independent vectors are n in Cn. So we now have n linearly independent eigenvectors in Cn whose dimension is n. What that means, these set of vectors are a form of basis. This is going to be a basis. What that means is these times any vectors are 0 for all x in Cn. That means the rank of this matrix is 0. Rank of this matrix is 0. What that means is this is not a 0 matrix. No. The rank of this one is 0. What that means is this matrix should be 0. If it's not a 0 matrix, if there is any non-zero entry in it, then the rank cannot be 0. But as you see, but this matrix is not a 0 matrix because this was a non-trivial Jordan block. It's not a 1 by 1 or anything. So here lambda was here, but ones are here. So if subtract of lambda I cannot be 0 because the size is not 1 by 1. This occurs a contradiction. So if it is a non-trivial Jordan block, then it is not diagonalizable. So we can say if we have a non-trivial Jordan block in the Jordan canonical form of a given matrix, then that matrix is not diagonalizable. I'll try to, in a very careful way, not waste time. 조심스럽게 다룹시다. Observation. If made, okay. First, A is similar to a direct sum of upper triangular matrices with simple, distinct eigenvalue lambda i's on main diagonals. Right? Main diagonals. Okay. Ti is upper triangular matrix with same eigenvalues like this. Which first, okay, if Ti is a matrix of size ni by ni, then we can reorder those blocks with these conditions, along with the size of each matrices, and the addition of those size of small blocks should be same as the full size of the matrix A. Okay. Okay. This is the process that we go to the final version of Jordan canonical form. Here's the sketch of the proof. By the Schur theorem, A is similar to an upper triangular matrix T prescribed order of eigenvalues on the main diagonals. Okay? So we just order the diagonal entries with the number of algebraic multiplicity of each eigenvalues. Okay? Then we realize if we multiply this matrix and inverse of this, alpha times ERS. ERS means it's a 0 matrix, only has 1 here, and R's low and S column, and all others are zeros. Okay, this is called the cell. Okay, if we multiply this matrix S and S inverse on right and left, then we can make this one entry here at R and S can be 0. You can easily check. If we multiply this matrix and this inverse of this one, then we can make this entry 0 when you have two distinct eigenvalues. This is a technique. So when you have the distinct eigenvalues, here lambda i's and here lambda j's, upper triangular matrix like this, then we can always make any beta here by this similar transformation. We can make this one to be 0 when you have a distinct eigenvalues. Okay, then you can easily check. That's why it's called observation. Okay. Well, now we think the upper triangular matrix Ti. Then this Ti is formed. Ti is what? Lambda i's here, lambda i's here, and we don't know what it is. This can be written as lambda I plus some strictly upper triangular matrix Ti hat. This is a strictly upper triangular matrix Ti hat. Okay, then S inverse TIS can be written in this way, and also can be written in this way. What that means is this Ti, the study of Ti can be done by study on Ti hat. Okay. So we only need to study this strictly upper triangular part because of the similarity relations. And also, most of information on TIs comes from the study on Ti hat. Particularly, most of the information on the Jordan block of Ti comes from the study on Ti hat. So we first develop the Jordan canonical form for this strictly upper triangular matrix Ti hat. Then we extend it to the original problem. Definition. Case superdiagonal of A. Here, this is called the superdiagonal. This is the second superdiagonal, and this is third superdiagonal, etc. Okay? So this is a diagonal, superdiagonal, the first superdiagonal and second superdiagonal, and this is case superdiagonal. Okay? Okay, then as you see here, Ti hat was all zeros here and some things are in here. This was the form. So now we think Jordan canonical form. This will correspond to some Jordan canonical form. So when we study the Jordan canonical form of this matrix, here all the eigenvalues are 0. So all the Jordan blocks will have the zeros as an eigenvalues corresponding on this. So we study the properties of the Jordan block whose main diagonals are all 0. Okay? So this is the first property. This is the Jordan block of main diagonals are all 0. If we multiply transpose of that block on left, then we have this matrix. You can easily check it. First, and then second, the piece power of this Jordan block will be 0 for all p which is greater than equal to k. You saw it before. Suppose we have 0, 0 here, like this. Then the square of this one will make 1 like this. And another power of this one, the cube of this one will make 0 like this. This is 3 by 3 matrix, Jordan block. Then cube of that is always 0 like that. Because whenever you to multiply the same Jordan block, then super diagonal we move forward. After certain number of power, there is no other entries than 0 in the whole block. This is what it says. This is very important fact. And also multiply the vector ei plus 1. That means there is 1 here and e plus I, and all I plus 1 here. There's only 1 on the position of I plus 1, and all others are zeros. Then it moves up, it moves down. The position of 1 moves down at once for i's between 1 and k minus 1. And also, for every vector x, I minus jk transpose 0, jk 0 times the vector x, we have this form. Now all the verifications are trivial. But with this fact that we can easily check, with this fact, we can have the Jordan canonical form theorem for a strictly upper triangular matrix A. Suppose A is strictly upper triangular, then there exists a non-singular matrix S and positive integers and i's whose sum is the size of the given matrix. Then S inverse AS is a direct sum of Jordan blocks whose diagonal entries are all 0, because A is a strictly diagonal, a strictly upper triangular matrix, and all eigenvalues are 0. So all the diagonal entries of the Jordan blocks should be 0. Okay. The proof here is we do the proof by mass induction. All we have to concentrate is by Schur's theorem, we find the T1 and T2 and Tk is like this. And all we know, we were able to make all the zeros other than these blocks. And then here, since since A is a strictly upper triangular matrix, then we know all the main diagonal entries of these are zeros. Okay. Now we think how many Jordan blocks that we have on this Jordan canonical form of T. Something like that. Okay. This is the theorem. We do only one blocks first. Okay. In each of them. We found here, as you see, we found n and r i's. Okay, we concentrate on one blocks first. Lambda, for example, lambda 1 and lambda 1 first. Then lambda, these are all zeros. We don't know that. But this one I get here. Yeah, we just concentrate only one blocks first. Each of the blocks first. See here, what's the problem? All we have to think here is just to find the number of Jordan blocks and the size of Jordan blocks. That's all we need. Okay? How we can do that? How we can do that? This is all we have to do. We use this and this. Okay? This is what I told you here. Here, lambda i's the power. What k and a minus lambda I k minus what the difference of these two and what the difference of these two numbers means. I explained it in a previous lecture. The difference of these two numbers means the number of Jordan blocks whose size is bigger than k. Okay. So all we have to think is just to calculate this relationship. So basically the proof for this strictly upper theorem, Jordan canonical for this strictly upper triangular matrix A is just comes from the property that we already examined. Okay. So all the detail comes from the understanding of the length of this. Okay. So the number of Jordan blocks on one eigenvalue lambda was defined as the geometric multiplicity of that eigenvalue. Okay. Let's say the algebraic multiplicity of lambda is m. We have m lambdas here. Okay. Then let's say the geometric multiplicity of lambda is equal to k. Then what that means? We have k linear independent eigenvectors corresponding to that lambda. Then what's the nullity of a minus lambda I? That's the k. Okay. The dimension of this, the solution set. What that means is the length of a minus lambda I is m minus k. But here, this is the same as A is the direct sum of the Jordan blocks, definitely. So this is the length of this direct sum of Jordan blocks minus lambda i's. That's m minus k. So this means this k is the number of Jordan blocks number of Jordan blocks that has lambda as a diagonal entry. What that means is, suppose we have geometric multiplicity k, that means we have k Jordan blocks on here. That's because of this, the meaning of the length of A minus lambda I. When we subtract A minus lambda I and find the length, then that exactly says that here this goes to all zeros and this goes to all zeros and this goes all zeros. That length was fully covered here, but when you subtract it, only these others are all ones here, like this. The length reduced by one here and one here and one here, like this. So it matches with the number of Jordan blocks corresponding to that lambda. This is important observation from that length argument. So, if A is diagonalizable, then geometric multiplicity and algebraic multiplicity for all eigenvalues should be same. Geometric multiplicity and algebraic multiplicity for each eigenvalues of A should be equal. So, we should have the exact number of Jordan blocks. We should have one by one Jordan block of n of the whole size. Okay. If not, we have 2 by 1, something like this, then it cannot be diagonalizable with all. So we should have 1 by 1 n 1 by 1 Jordan blocks. That means we should have geometric multiplicity. We should have Jordan blocks as many as algebraic multiplicity of each of the eigenvalues. What that means is geometric multiplicity of each eigenvalue should be same as algebraic multiplicity of each eigenvalues. Okay. When it has this condition, we say A is simple. A is simple. A is a simple matrix. When we say A is simple, it means geometric multiplicity and algebraic multiplicity are all same. Okay. The proof is just the easy argument. Since we have n, when we have n by n matrix here, if we have algebraic multiplicity and geometric multiplicity are same, then we have what? N linear independent eigenvectors. So it's diagonalizable. When it's diagonalizable, we have Jordan block. So n, which means algebraic multiplicity and geometric multiplicity are same. So it's an easy exercise. Next. When A is a direct sum of AIs, then length of A should be same as summation of the length of each block. When A is similar and lambda is an eigenvalue of A and the geometric multiplicity of lambda on A is K, then if they are similar, so suppose lambda is an eigenvalue of A, then lambda should be the eigenvalue of B, because the similar matrix should have the same set of eigenvalues. But also, geometric multiplicity of lambda on B is the same as the geometric multiplicity of lambda on A. This is important. When it's similar, same eigenvalue has the same geometric multiplicity. What gives us, this comes from, since they are similar, they have same Jordan blocks. Then number of Jordan blocks for lambda for A is same as the number of Jordan blocks for lambda on B. But that means its geometric multiplicity of lambda on A is same as geometric multiplicity of lambda on B. It's very easy. But this is very important on our argument. Similar, it is same Jordan block. For each eigenvalues, they have the same geometric multiplicity. Okay, here now we have here now we have a real Jordan canonical form. Suppose A is an n by n matrix, then there exists a non-singular matrix S such that S inverse AS is a Jordan canonical form of A, which is a direct sum of Jordan blocks. And also, this J is unique up to the permutations of the blocks. We can commute the location of each Jordan blocks. In case A is a real matrix, then and every eigenvalues are all real, then S and J can be chosen as a real matrix. Okay? Yeah. When the eigenvalues of A are real, then all the calculations are done in real numbers. So S and J here, the all eigenvalues, these are reals. Here's are 1 or zeros. So this definitely this is a real matrix, and A is a real matrix. Then when you multiply the eigenvectors, and this should work. This calculation should be done all in real. That's what it says. Okay. Anyway, the 3 comes directly, and the first one comes from there is for each Jordan blocks. For each blocks, we can do so first we by the previous lemma, we know this matrix A is similar to the direct sum of upper triangular matrices first. Then we think this is strictly upper triangular matrix for these each blocks. Okay. Then we find the non-singular matrix SI. SI inverse times this matrix times SI is the Jordan, the direct sum of Jordan blocks for that particular eigenvalue lambda I. This all comes from the previous observation. Then we form an n by n matrix S by multiplying the S naught times direct sum of all this. Okay. Then we can get this. Okay. Then this is done. This is done. J is unique up to permutations of the blocks. For the uniqueness, what you have to show is suppose there are 2 Jordan canonical form for a given matrix of the permutation, then we show they are same. Here is the proof. Suppose we only consider for the one block first. Suppose the eigenvalues of J and eigenvalues of J tilde is only lambda. Then we know this and j and j tilde is similar. And j can be written in this way, and j tilde is written in this way. So this is a Jordan canonical form of one single eigenvalues first. Then we show there exists a permutation sigma such that one each of these Jordan blocks is one of these. By just changing the order, then it will show the uniqueness. And the same argument works for all different Jordan blocks. And block diagonal matrices, we don't have to worry about all other blocks because all the calculations can be done by each blocks. So all we have to do is show the existence of permutation that makes a correspondence on Jordan blocks. Okay, proof. Without loss of generality, we give an order on ni's and mi's. We give an order. Then we have to show. So, for example, we just give it. Let's give an order with so arrange the Jordan blocks in order of size. The bigger one first and smaller one. Bigger ones first and small. This is the size of the Jordan block. The bigger ones first and smaller one later. Something like that. Then actually we can show this order. So for example, sigma of ni is mi. So this gives us the permutation sigma like this. Because we can show each of n1s are same as n2, n2 is m2, and nk is mk. We can show that. We can show that. Then what that means is this, isn't it? Proof. By the way of contradiction, suppose there are some ni and mi. They are not same. If the size are, there are some matrix which has a different size in the middle. Then there exists, suppose there exists the smallest L, then NL is not same as ML. So there are some block which has a different size when you order in the size. Without loss of generality, assume NL is bigger than, strictly bigger than ML. Okay, then think about the power of NL first. NL power of MI is bigger than, is equal to 0 for all I greater than equal to L. Because Ni is smaller than, Mi is smaller than NL. So, the power of the matrix NL is equal to 0. But the power of this matrix to the ML is not a 0 matrix. So this is a 0 matrix, and this is not a 0 matrix. Now we go back to the original matrix, J minus lambda I and J tilde minus lambda I. The power, take a power ML on both matrices. Then is the power of on the direct sum of the block diagonal matrix. So we can think the direct sum of the power of on each Jordan blocks and take the direct sum of it. Because we are dealing with the Jordan blocks. When you have a power here, then that means same as this one. This is what it says. Okay? So here, as you see here, this and this has the same Jordan block with same eigenvalues and same size. The powers are all same. Even if you take the power, it just moves on. But what about this? This is a zero matrix, as you see here, but this is not a zero matrix. This is the same matrix, and this is not the same matrix. But these two matrices should have the same length. This cannot have the same length. This is one zero matrix, and this is not a zero matrix. This is the same matrix. Length should be the summation of the length of each blocks. So those lengths cannot be same. What that means is the length of this one is smaller than this one. But these are similar matrices. So these are similar matrices. See? So the length should be same. Since they are similar, this strictly inequality gives us a contradiction. Okay? This gives us a proof. So Jordan canonical form is unique up to the permutation. Okay. Next. 이게 굉장히 민감해서 조금 치면 바로 그냥 페이지를 바꿔버리는데 그건 잘못 만든 것 같다. 이렇게 바꾸고 가면. Okay, next. Corollary. This is just a modification of Jordan canonical form. If when we have Jm of lambda epsilon and lambdas are here and epsilon instead of 1, here then we know the notation like that. Then for an arbitrary matrix A and for an epsilon, positive real number epsilon, there exists a non-singular matrix S. S inverse AS is similar, is a direct sum of this form of blocks from diagonal matrix. What this means is we can make the norm of that matrix is smaller than what it has. Actually, what that means is for each Jordan block, lambda minus lambda, the Jordan block, lambda minus lambda I. Here, the epsilon like this. And here, then what that means? We can make this norm as small as possible. This is a small modification because if we multiply this d epsilon matrix and the inverse on the other side, then we can just make this norm as small as possible because all the diagonal entries are gone and these are left on this. And this is a block. All the process are done on the block diagonal matrices here. So each we make this one as small as possible and this one smaller as possible, norms on this size. Then what that means is we have lambda 1 to lambda k here, and here most of them are 0, and here we can have all the epsilons or 0. Epsilon can be epsilon or 0. So this norm can be just the same as the addition of absolute value of the lambda i's. This is just a small modification for that. So we now have a full control of the off-diagonal entries by using the similarities. Okay, so now we are in the stage that we organize what we have studied. Okay. Every matrix A is similar to A transpose. I know. Yeah, A is similar to A transpose over any matrix over any algebraically closed field. Okay, we want to show this one. For a matrix of any size on any algebraically closed field F. What we need to show is, if we show JA is similar to JA transpose, this is done. If we show this one, then this is done. Isn't it? Because A is similar to A transpose, A is similar to J Jordan canonical form of A, and A transpose is similar to the Jordan canonical form of itself. So this is what we want to show. See here, for each Jordan block, J, if we multiply this per diagonal matrix on both sides, then we can easily see this once moves to the subdiagonals from the superdiagonals. So each Jordan blocks are similar. So let lambda Ji of lambda I be a Jordan block, and Jordan block of a Jordan matrix of A is a direct sum of those Jordan blocks. Then JA is similar to JA transpose, which is the direct sum of those, because this is the direct sum businesses. So we make direct sum of the similar matrices, the non-singular matrices SIs, to form big matrix S that makes S inverse JA S equal JA transpose, like this. Then this is shown, so this is done. So this is a very simple but important thing. So in order to understand this relationship, we should have knowledge on the Jordan canonical form. Okay. Okay. Yeah. The proof is, like I mentioned, we found the SIs for each of the Jordan blocks, and we form a big matrix S as a direct sum of those small SIs. Then we see that's true. Then we show A and A transpose are similar by showing the Jordan canonical form of those two are similar. A is similar to Jordan canonical form. This is similar to the JA transpose, which is similar to A JA transpose. Jordan canonical form of A transpose, which is similar to A transpose. This is the proof. Okay. Very nice. If we know about Jordan canonical form, there are alternative ways on the proof. As you see, as I mentioned, Jordan canonical form is completely determined from the information of the length of these matrices, the series of this, when lambda I is an eigenvalues. And length of this is same as length of this on A transpose. These informations are this is same for all case. Jordan canonical form is completely determined by these informations for each of case. And those are same exactly. But that means the Jordan canonical form, which is formed by the information of this series of numbers are same, which says A and A transpose are similar, because they should have the same Jordan canonical form, because they have the same information on the length of A minus lambda I to the case power. Okay, this is another way of proof. Okay. We summarize it. For one eigenvalue lambda, the Jordan block and its transpose are similar. And A is similar to A transpose because of that. And A conjugate is similar to the A conjugate transpose, because A is similar to the transpose. When A and B are Hermitian, then AB is Hermitian if and only if AB is commute. And F is normal matrix. Suppose F is a set of matrices that are commute. Of normal matrices, then F is simultaneously unitary diagonalizable, because Hermitian matrix is normal. When F is a Hermitian, is a commuting family of Hermitian matrices, then F is also simultaneously unitarily diagonalizable. And some more informations. The two diagonal matrices whose diagonal entries are same, then those two matrices are permutation similar, because by permutation we can relocate the diagonal entries, the diagonal matrix. Suppose A and B are diagonalizable and the eigenvalues are same with the same algebraic multiplicity, then we know A and B are similar. Diagonalizable and the same eigenvalues with the same algebraic multiplicity. Then what that means is this is just the same meaning of a rewritten of the first statement. A is a direct sum of AI's. Then by the permutation we can just always reorder those block matrices. And this matrix is similar to this matrix, this 2 by 2 matrices. And we saw this one in chapter 2 a lot. And rank of A is same as rank of A conjugate. If A is a real matrix, then the case power of A minus lambda I, the rank of it is same as conjugate, and the same with the rank of A minus lambda conjugate I to the case power for every case. What this means is, if lambda is not a real number, then Jordan block of lambda, if it exists, then the Jordan block of lambda transpose should exist as well. Understand? So if you have something here, then this should follow. So that gives us a fine examples. Okay, here. This is the algorithm of the Jordan canonical form, finding Jordan canonical form. First, find the eigenvalues and find the corresponding eigenvectors, and find the rank of all this for each ki's. Then we know we can find from those information the Jordan canonical form. Then we know S inverse AS is equal to JA. Finding S can be done by generalized eigenvectors. We have learned, since you have a Jordan canonical form first, and you have the eigenvalues here, and you know the algebraic multiplicity of it. So from here you know the geometric multiplicity of each eigenvalues. You know the size of it, so you know what's the complete sequence of generalized eigenvectors for each Jordan blocks. Then you can find Q. That makes Q inverse AQ is Jordan. This is the homework that you have done already. 성태, did you do? Find the series of complete sequence of generalized eigenvectors. I told you you do the 3 problems for finding Jordan canonical form and the matrix Q. Jordan canonical form problems. That was a part of the previous homework problem, to find the Jordan canonical form and the matrix Q. Okay. Anyway, if A is a n by n matrix and these eigenvalues are distinct, then A is diagonalizable if and only if geometric multiplicity of lambda I is same as algebraic multiplicity of lambda i's for all I. And this is what we already proved, and this is a review. Okay. And these are the problems that I already explained. So suppose I give you some information on the eigenvalues and geometric multiplicity. Then we should be able to find the Jordan canonical form, isn't it? Here we have eigenvalues 1, 1, 2. The algebraic multiplicity of 1 is 2. And geometric multiplicity of eigenvalue 1 is 1, and geometric multiplicity of 2, eigenvalue 2 is equal to 1. So 1 has 1 Jordan block, and 2 has only 1 Jordan block like this. So Jordan canonical form can be given by only these information. So all you have to know is just geometric multiplicity and algebraic multiplicity and eigenvalues. For example, here it's a 4x4 matrix. All eigenvalues are 1, so Jordan canonical form should start with this one. But geometric multiplicity of 1 is equal to 2. Then we have 2 choices. There are only 2 Jordan blocks in here. So we can have 3x3 and 1x1, or 2x2 and 2x2. That's the only 2 cases. If we give order, then that's the only 2 cases. For example, here, we have 5x5 matrix with eigenvalue 1, 1, 2, 2, 3. 1, 1, 2, 2, 3 like this. And geometric multiplicity of eigenvalue 1 is 1, and geometric multiplicity of eigenvalue 2 is equal to 1. Then we have 1 Jordan block for eigenvalue 1, and we have 1 Jordan block for eigenvalue 2. And for 3x3, and for the eigenvalue 3, we don't even need to find it, because it's just 1 by 1, something like that. So these are all the information that you need to figure out the Jordan canonical form of the given matrix. And all these can be found by examining the rank of the matrix A minus lambda I and its powers. I made a Java tool to calculate the eigenvalues and also A minus lambda i's and the powers of it and the rank of it. So even without any softwares, commercial software, we can do that. But now I gave you some homework that you can use a scientific workplace to do calculation, which is based on the Maple software. You can find the eigenvalues and the rank of the matrix and powers of it. There are many other tools that you can use. And so I give some matrix, you should be able to find the Jordan canonical form by hand or by using the softwares. For example, if I give you a matrix like this, then you should be able to find the characteristic and eigenvalues, and then you know the algebraic multiplicity of each eigenvalues. Then you can find the lengths and another lengths that give us the geometric multiplicities that will give you the Jordan canonical form. This is very interesting and very nice way of finding a canonical form. There are many other canonical forms, but as you see, this is the most easiest, simplest form. I explained it, the finding of general eigenvectors in very detail last week. This is the primitive form of it that I already explained it to you. You should be able to find how to with this Q by using the generalized eigenvectors. Complete sequence of generalized eigenvectors to find it. And the next thing is about, next important concept is about the polynomial and matrix. That's the minimal polynomial. Minimal polynomial. 아직 안 끊어지고 지나가고 있는 것 같지 않아? 리프레시해서. Okay. 자, I think it's gonna work. Annihilating polynomial. P of x is a polynomial and A is a matrix. If P of A is a zero matrix, then we say this polynomial annihilates A. And we say P of x is an annihilating polynomial for A. When A is an n by n matrix and QA of x annihilate the matrix A, then we call it's a minimal polynomial if A annihilate any polynomial P of x. This it is QA of x divide any annihilating polynomial for A, then we call this is a minimal polynomial. And then monic. A monic polynomial that divide any annihilating polynomial P of x for A matrix, then we call that monic polynomial P, QA of x, be a minimal polynomial. Okay? So minimal polynomial is the polynomial annihilate the matrix A, but with the smallest degree. Okay? We know there exists such a polynomial because the degree, because of division algorithm. Now there exists a certain polynomial, and there is the smallest polynomial that divides. If there is no, then P of x is itself can be minimal polynomial. So this is the existence of the minimal polynomial is guaranteed by the division algorithm. Okay. And minimal polynomial, the existence of the minimal polynomial was guaranteed. So we now give the definition, the formal definition of minimal polynomial. Suppose Q of x is a polynomial and A is a matrix, and Q of A is equal to 0 is a monic polynomial of a minimal degree, then we say A, the Q of X is a minimal polynomial of A, and we write it as a QA of X. Okay. Here is the properties of a minimal polynomial. Every similar matrix has the same minimal polynomial. Suppose A is similar to B, then there exists a non-singular matrix S that makes this. Then QA of B is like this. This is zero matrix. What that means is this divides this. QA of B. Okay, yeah. And QB of A can be written in this way. And this is QB of B here, like this. QA of B is equal to 0. So yeah, QA of A is definitely this was 0. And but this QA of B is also an analytic polynomial. That means what that means. We already know Q of B, this one divide is equal to 0. So it satisfies it. That gives us this. That means there exists a unit alpha, which makes this and this can be same by just multiplying a unit alpha. But these are both monic polynomial, so alpha should be the one to make it same, because the leading coefficient is 1. So they should be same, which says those are same. So similar matrix, they have same characteristic polynomial, and also they have a same minimal polynomial. This minimal polynomial is a very important concept in the research. You should know that. Suppose QA of X is a minimal polynomial of A, then QA of lambda is equal to 0 and only if lambda is an eigenvalue of A. Yeah, you know it. Yeah. Definitely. Because this minimal polynomial divides the characteristic polynomial. So if it's a 0, then it satisfies, the lambda satisfies the characteristic polynomial. So lambda should be the eigenvalue of A. If A is an eigenvalue, lambda is an eigenvalue of A, then there exists an eigenvector X. Then QA of A times eigenvector X is equal to 0, but this is a scalar. And you plug lambda there. This is a non-zero vector times scalar is equal to 0, but that means this is 0. So when you have an eigenvalue, then it satisfies the minimal polynomial as well as characteristic polynomial. Here's a lemma. Say we have one Jordan block. For one Jordan block, characteristic polynomial and minimal polynomials are same. One Jordan block. Lambda, 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 1. For this Jordan block, characteristic polynomial and minimal polynomials are same. Furthermore, if the size of that matrix is n by n, then minimal polynomial and characteristic polynomial is just t minus lambda to the that size. And we can easily, since for this matrix, lambda I minus am of lambda, the m's power is equal to 0, but any smaller one cannot be zeros, because this super diagonal just moves up until this is the first one. That's the smallest. So this polynomial is the minimal polynomial. from this lemma, we can find the relationship with the companion matrix and also the hypercompanion matrix and the relationship between them. Usually, in a master's level class, you learn up to companion matrices, not hypercompanion matrix yet. Okay, lemma 2. If J is a direct sum of Jordan blocks, then this Ti minus lambda to the m's power, where m is the maximum of this, is the minimal polynomial for that Jordan canonical form. Do you know what this means? We have Jordan blocks, small and something like this. Okay. What this means is the minimal polynomial here. This is m. So m1, m2, m3. Then when lambda I minus j, the power is going to be 0. When you multiply 1, 2, 3, 4, 5, then before you reach the maximum size of this, you still have some ones here, even though the others are going to be a zero matrix in an earlier stage. But when you reach it up to that largest size of Jordan block, you find the zero matrix at first. So the minimal polynomial of the power of the minimal polynomial is going to be the size of the largest Jordan block corresponding to the eigenvalue lambda. Do you understand? What this lemma says is this power m is the size of the largest Jordan block corresponding to this lambda. Okay? Because the smaller ones are gone before you reach that one. That's the first one. From here, we can have the following theorem. Okay? The theorem. Suppose the sigma of A is lambda 1 to lambda m. We have m distinct eigenvalues. Then QA of T, the minimal polynomial, is a product of these for each distinct eigenvalues. When this Ri is the largest, the size of the largest Jordan block corresponding to the lambda i's. We call that's the index of lambda I. Okay? This is because J of A and QA of A is QA of JA. This is going to be 0 when we reach it the very first on the largest size of the Jordan blocks. Before that, it cannot be a zero matrix. Okay? It's all because of the definition of the minimal polynomial. Minimal degrees monic polynomial. So the largest Jordan block. So minimal polynomial has most of the information on the largest Jordan blocks. So when a matrix is given and you have a characteristic polynomial and you have a minimal polynomial here, then from here, at least you know. From here you don't see anything. you only have a triangular matrix. But here, you see the largest Jordan block and missed. Suppose the lambda i's are distinct eigenvalues of A, and A is diagonalizable, then this should be all ones. Okay, minimal values. Because the largest size of the Jordan blocks are all ones for the diagonalizable matrix. So it should be all ones. So linear vectors. This is a definition of companion matrix. This is the definition of companion matrix. Suppose you have any polynomial. You have any polynomial like this. Then here is a matrix. All the coefficients of this matrix are here. All the subdiagonals are all ones. This is called the companion matrix of this polynomial. Important fact is this: every monic polynomial is a characteristic polynomial and minimal polynomial of its companion matrix. Every monic polynomial is a characteristic polynomial and minimal polynomial of this companion matrix. This is the fact. This fact can be easily checked. See the textbook page 146. It's well written. On that. So this. Now you can think the matrix from a given any polynomials, and already you know pretty much of information of it. But that means it has one Jordan block as well. Okay. Here we are very close to the end. Yeah. Suppose A is an n by n matrix, then its characteristic polynomial PA of T matrix. So matrix A has a characteristic polynomial here. Then what it says is from here you can have the companion matrix. Then this companion matrix of this characteristic polynomial is similar to this original matrix A. This is what it says. Okay? From given a matrix A, we can think of the characteristic polynomial. Then from the characteristic polynomial, we can think of a companion matrix. This companion matrix is a matrix which is similar to the A matrix. This can be shown. The way this is possible when characteristic polynomial and the minimal polynomials are same. Okay? This is if and only if condition. And here is some motivations why we study minimal polynomial. Why? For the small size matrix, if we know minimal polynomial, we can easily find the Jordan canonical form. And also, for study of matrix function, this minimal polynomial is very powerful. Matrix function was a popular topic of research before. Minimal polynomial was a very big tool. And also, the relationship with the companion matrix give us a Frobenius normal forms which comes from elementary divisors, and all other normal forms of a given matrix. Okay? But now, if we know the Jordan canonical form, then we can easily find the minimal polynomial without any difficulties. Okay, I told you some motivations of minimal polynomial. This is the way how we use minimal polynomial. Suppose A is a matrix like this. Find E to the A. How you can find it? How you do it? You can do it by the way that you learn from the ordinary differential equations. For solving linear differential equations, you have to do these kind of computations. But if you know the minimal polynomial, we can use it in the way that we like to do. Here, find the minimal polynomial. Since the characteristic polynomial is this, and the minimal polynomial is this, because it's a distinct eigenvalues. So this is the minimal polynomial and characteristic polynomial. Then we find alpha and beta that makes the remainder of that is equal to 0. It's all from the division algorithms. Since this set QA of A is equal to 0, okay? What that means is A square, this is the degree of this one is 2. Should be written as alpha plus beta A, isn't it? A square should be written in this way. So we go. And this addition should be 0. So we just do some calculation. We put some numbers. We have the eigenvalues 5 and minus 2 here. Using that, we since this should satisfy it, so we can by using the properties of minimal polynomial, we should be able to form a system of equation to find this coefficient alpha and beta. We find alpha and beta by solving the linear system of equation. Then we use this and alpha and beta to find E to the A. Okay. I will show some others. For example, suppose A is this matrix, and find the minimal polynomial. Then we can find sine pi of A. This is a way of finding a minimal polynomial. Q of A can be written in this way. The degree cannot exceed the size of that matrix. So for try the polynomial which is a degree 1, and degree 2, and degree 3, none more than degree 4, we know it. Okay? So for degree 1, if it's a degree 1, then it should satisfy this polynomial. But we cannot find A here. So the minimal polynomial is not the polynomial of degree 1. Think about the polynomial of degree 2 and try to find this coefficient. But we know there is no such a thing. We can easily put some numbers here to compare the couple of coefficients here. We know that doesn't work. So there's the minimal polynomial is not the degree of the polynomial of degree 2. For the polynomial of degree 3, yeah, we think we plug in some point, we plug in some. We can find A square and A and I, and we can compare a couple of entries. to check whether it is same as this. Okay, then we can easily. There are so many entries that we can compare. That how many equations? At least we have 16 equations. How many unknowns that we have? We have 3 unknowns. So we can easily find some numbers that satisfies these conditions. We have more information. Then we have 0, 1, and 0 as the coefficient on these polynomials. So what that means is we have a minimal polynomial which is this t cube minus t. Okay? So this is a minimal polynomial. Okay, then find the sine pi a. How? Okay, r of t is should be sine pi t because all the previous terms are gone. So remain the theorem. All the polynomial, all the terms with the degree higher than the degree of the minimal polynomials are all gone. So all we have to worry about the remainder terms like this. Okay, so remainder term is sine pi t is r of t, and r of t is the polynomial of this. Okay, then plug then sine pi of t is this, and this satisfies these conditions. So from here we find the alpha, beta, gammas are all zeros. That makes this sine pi a, which is r of a, is a zero matrix. So answer is this is a zero matrix like this. Okay. So find the minimal polynomial, and all you have to do is to think about the remainder, which is the degree of polynomial less than the degree lower than the minimal polynomial. Okay, for the matrix A, or we can also do the cosine pi as also the same thing for the cosine pi A. Find the minimal polynomial by the similar way that we did. Try the degree of polynomial, the polynomial degree 1, 2, and 3. And here we found the minimal polynomial of degree 3. The remainder term is what we need to think. Then we plug the numbers to find this coefficient alpha, beta, and gamma. Then cosine pi a is I minus 4i plus 2a squared, something like this. So this minimal polynomial has many meanings and powers on the matrix computations. Now, this is another way of doing the similar things by Jacobi identities, which you learn from the ordinary differential equations. Okay. This is a review of what we have learned. There are more on the canonical forms, such as Smith normal forms and Frobenius normal forms, and many others. All this research was done before the Jordan canonical forms. It used determinantal divisor, invariant factors, and elementary divisors. Those informations can be found from page 154 and 155. But most important things are the Jordan canonical form. That's what we have covered. There are other forms of canonical forms, but I think it will be enough that you know about the Jordan canonical forms. And there are some other forms of canonical forms. This is a definition of how a hypercompanion matrix matters. And then the chapter 3 are mostly covered. And the last section of chapter 3 is a LU decomposition. For the LU decomposition, you already have covered quite in detail, not only at the elementary linear algebra, but at the matrix theory, LU decomposition, LDU composition has been quite well covered. I will go through once more, but chapter 3 is mostly done. Any questions on chapter 3?